So in this presentation, we are going to be focusing on what a derivative is and some general aspects generally associated with derivatives of functions. So to start off, we're going to start off simple with what is a derivative, like what's its definition. So a derivative can be defined as the instantaneous rate of change of a function or the slope of a tangent line at a given x value.
Okay, so that brings us to average versus instantaneous rate of change. And what really does that mean? So the average rate of change is going to be found through this equation, which you might recognize as the change of y over change of x. And this is just in a different form with plugging in the x values to the function. And let me get my marker out here. As you can see, our 2 points here are here and here. And when we're finding the average rate of change, basically what we're doing is we're finding the rate of change of the line directly between these 2 points. So the rate of change of this line right here. And then when we go to instantaneous rate of change, this is where we get into derivatives. So the instantaneous rate of change is the rate of change at a very specific point. And it's always going to be tangential to the function. As we can see here, it is just on the outside. And we can find it through the derivative of the function. And the way that we find the derivative, one of the ways is the definition of the derivative, which we're going to get into on the next slide. But an important concept to know is that when we're talking about h in the definition of the derivative, we're talking about the difference between like these 2 points here. So let's say we were trying to find the instantaneous rate of change of a specific point on this graph right here. H in the definition of the derivative would be the distance between these points getting closer. Let's see, closer and closer together until the distance between them is 0, and you get the tangential slope.
Alright guys, so we're going to transition to the whiteboard here, and as you can see, we're going to start with a pretty easy example. So what this is asking us to do is we need to find the average rate of change of the function f of x, which is 3x squared plus x, over the function 0, 5. And these are all x values, obviously. And so basically what we're doing here is, let's just say that this is 3x squared plus x. It's obviously not, but for simplicity's sake, we're going to say that it is. What we're doing is we're taking these 2 points, 0 and 5, and we're going to find the average rate of change between them, which is going to be the slope of this red line right here. And the way that we do that is we just do the y values over the x values. So what that's going to look like is we're going to do f of 5 minus f of 0. These are our change, that's going to be our change in y values, over 5 minus 0. So we're going to plug in our 5 and our 0 to our f of x up here. So this is going to be 3 times 5 squared plus 5. And all of this is minus 3 of 0 squared plus 0, which obviously this is just 0, all over 5. This is going to give us 75 over 5, which just reduces down to 15. Which is our average rate of change for the function 3x squared plus x over the interval of 0 to 5. All right, and we're moving on to the next example. And so here we're going to find the instantaneous rate of change of the function f of x equals 3x squared plus x for the point x equals 3. And as you can see, this is the exact same function that we used for the last one with the average rate of change. And this is so you can kind of see the difference between average and instantaneous. So on the average, where we had these 2 points, 0 and 5, we were finding the average, which is, as you recall, the slope of that line right here. However, with the instantaneous rate of change, what we're doing is we're finding the slope of the line exactly where that point is, where it's tangential to the curve. So what it's going to look like is we're finding the rate of change of this green line right here. And the way you can kind of think about it is that you're taking these 2 points and you're making the difference between them so small that the slope kind of pops up on top of the curve and becomes a tangential slope. And that idea is kind of explored in the definition of the derivative as h is going towards 0, which is the difference between those 2 points. But we're going to get into that at a later time. So to find the instantaneous rate of change of something, what is the instant rate of slope? What is a tangential line? Well, that's just the derivative. So what we're going to do is we can either use the definition of the derivative, or if we know just normal power rule, we know that the derivative of f of x is going to be 6x plus 1. And that's just basic power rule using this. And then we can plug in f prime of 3, which is going to be 6 times 3 plus 1. And that is going to give us a slope of 19. And 19 is going to be our instantaneous rate of change for the function of 3x squared plus x on the point x equals 3.
Oh my god, he's speeding.
Hello, officer. How are you this morning?
Do you know how fast we were going?
Actually, I do. Thank you. See, if we take the average rate of change of my speed using this function here, this formula here, and we do some math, we can see that I was actually, on average, below the speed limit.
But my radar gun could detect your instantaneous velocity, and it registered 55 miles per hour.
Oh no, officer, it's not what it looks like. I can't go to jail again. I gotta pay child support.
Yeah.
Alright, so that brings us to the definition of the derivative. And this is the definition of the derivative. It's kind of also known as the long way to find the derivative. But you might be noticing here, oh, this isn't really like an equation or anything, this is a limit. And this is tying back to what I was talking about before, with h being the distance between 2 points, and then becoming so close that they basically almost become 1 point, and creating a tangential line to the graph. So when we're trying to find the derivative of a certain function f of x, we'll plug it into this function here. This limit here. Do some algebra magic, and boom, get our derivative. And we'll have some example problems on that. And actually, let's look at some example problems now. Alright, and the definition of derivative at a point is also a limit. And basically what this is doing is almost the same thing as the other definition, but what this is doing is giving us the definition of the derivative at a point. So plugging in our values here is going to give us isn't going to give us the f prime of x function. It's going to give us f prime of a certain number, which in this case, showing here, it would be c. So a real-world application of the definition of derivative would be to, let's say you're given a function f of t, and that's basically going to represent the population of a certain country, and time is going to be in years. T is going to be in years. So we can use the definition of the derivative in order to find that the derivative, the function f prime of t, and we can use that and plug in a certain year and find the population's rate of increase on that specific year.
Alright, so in this problem, we are given a function, which is going to be f of x is equal to 3x squared plus 2. And what it's asking us to do is to find f prime of x, which is simple enough, but it is using the definition of the derivative. Now, 90% of the time in this class, you'll be able to use power rule and your different derivative rules and be just fine. But if it ever asks for specifically setting it up in this way, this is going to be how you do it. So, as we know, the definition of the derivative is going to be the limit as h approaches 0 of this whole blurb, which is f of x plus h minus f of x all over h. And so we're going to put this f of x into here, and we're going to do some manipulation with the h and canceling terms to be able to find f prime of x. So I'm going to do that in a different color here. So when we plug this in, what we're going to have is we're going to have the limit of h approaches 0 of 3 parentheses x plus h squared plus 2 minus 3x squared plus 2 all over h. And once we simplify that down and square this inside term and everything, we're going to end up with this big long blurb, which is going to be the limit of, as h approaches 0, of 3x squared plus 6xh plus 3h squared plus 2 minus 3x squared minus 2 all over h. And as you can see here, there we have some terms that are going to cancel each other out, namely 3x squared plus 2 minus 2. And what it's going to leave us with is the smaller version of the limit as h approaches 0 of 6xh plus 3h squared over h. And what we can do here is we can take out the h. So this is going to go to h times 6x plus 3h all over h. And so we can cancel out these terms. And then we can solve the limit of h approaches 0 of 6x plus 3h. 0 times 3 is 0. So our limit is going to turn into, our limit as it approaches h equals 0 is just going to be 6x, which is going to be our f prime of x. And we can check that using our power rule. So if we look here at 3x squared plus 2, we can just bring this down, subtract the exponent, the 2 goes to 0, and f prime of x according to our power rule is also 6x. So as we can see, this is a bigger, more roundabout way, but we're going to need to know how to do it in the future for different definition of the derivative problems. Questions like these are really common, where you just have a specific instance of the definition of the derivative and it just says solve, or perhaps it literally is just this part. And you might be wondering, what do I do with this? Well, what you're going to do is you're going to basically, the thought process behind it is that you need to find f of x and then take the derivative of it, because that's all this is. It's taking f of x and it's plugging it into the definition of the derivative, which will output the derivative. So what we want to do is find f of x and then use the product rule and your other derivative rules to just get the derivative a lot easier. So as we know, the base function, or the base limit for the definition of the derivative is f of x plus h minus f of x over h as h approaches 0. And as we can see, this is following a very similar sort of structure. And from what we can tell, we can see that cosine x is the f of x here. So f of x is equal to cosine x. And then from here, we can just use the rule that we know, that f prime of x is going to be equal to negative sine x. And that is how you solve one of these problems. So as you can see, we have our limit here, but looking at it, you might say, whoa, 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 we don't have our f of x. There's just a 1 here. What do we do? So what we need to recognize is that we still have the function here, and which is going to be x plus h. We just have an actual x value. So looking at it, oh, well, sine of, and the x is going to be pi over 2, and sine of pi over 2 is just equal to 1, which is right here. So that makes sense. So really what this function is sine pi over 2 plus h minus sine pi over 2. So now we know that our function, our f of x, is sine of x. And so now we can find the derivative, but because we have a value for x, we have to find the instantaneous rate of change of sine of x at pi over 2. So we're going to take the derivative of sine of x, which is going to give us cosine x, and then we do f prime of pi over 2, which is going to be cosine of pi over 2, which is just 0. So that's how you would solve it if you already have an x value plugged in. You have to figure out what the x value is making this right here, and then kind of solve as normal, and then plug in your x value at the end.
So up next we have connecting continuity and differentiability. So the general rule that we're going to want to look at here is differentiability means that a function must be continuous, or it implies continuity, but continuity of a function does not always imply the differentiability of that function, or the ability to take the derivative at any point. So if you take a look at some specific rules, we can dive deeper into this phenomenon. So rule 1, if f of x is differentiable at a point P, then f of x must also be continuous at that point P. So this makes sense if you take a look at a function like this one. When you take the slope at a point, it means that that point must exist, or else you wouldn't be able to take the slope there. Our next rule, if f of x is continuous at a point P, you won't always be able to take the derivative at that point. In this case, you'll need to check to see if the function is differentiable. So, for example, this function right here is continuous. You can draw it without ever having to take your cursor or pencil or pen or whatever you're using to draw it. You won't have to pick that up when you're drawing it. However, if you look at this point, x equals 0 right here, there's a cusp. And what that means is basically you can draw multiple possible slopes here if you were to take the derivative at that point. Because there's multiple possible slopes, it's not differentiable even though it is continuous. Now the third rule that we have, if f of x is not continuous at a point P, then it will never be differentiable at that point. This makes sense because if you look at this graph, there's a whole discontinuity here. There's no point there. Therefore, you cannot take the derivative or find the slope at that point. Here, there's a jump discontinuity. If you were to take the derivative, you could get a slope here, and a slope here, but the slopes would not be the same, so you cannot take the derivative at this point. Here, there's an infinite discontinuity, so there's really no point to even take the derivative at, so it's not differentiable there either. So when a function is not continuous, it is also not differentiable. Let's take a look at some practice problems.
So let's take a look at these first set of graphs. Are these graphs differentiable? Why or why not? So this first graph right here, it is continuous because there is no break in the graph. You can trace it and your pencil won't come off the paper. So we know it's continuous, but remember, continuous does not mean it's differentiable. And if you look right here, it has a cusp. So if you try and take the slope of the line at this point right here, you could end up with multiple different possible slopes. Therefore, although this graph is continuous, it is not differentiable. This graph has a very similar situation. You can trace it, and you won't have to take your pen off the paper, or whiteboard in this case. So it is continuous. However, if you look at this point right here and try and take the slope, you could get multiple possible ones, so it isn't differentiable at this point. So although the graph is continuous, it is not differentiable. Okay, so let's take a look at this second graph. Is this graph differentiable? Well, if you look at it, it is continuous because you can trace it and you won't have to take your pen off the paper. But remember, continuity does not necessarily mean differentiability. So if you look at this graph, it actually has a vertical slope at this this point right here. So because it has a vertical slope, the slope is undefined, and therefore it is not differentiable at this point right here. Therefore, although the function is continuous, it is not differentiable. So let's take a look at this third set of graphs. Are these graphs differentiable? Why or why not? So let's take a look at this first graph. This first graph, if you look at it, you cannot draw it without picking up your pen while drawing it. So if you look at it, that means it's discontinuous. And if you notice, the type of discontinuity right here is a jump discontinuity. Because it is not continuous, it automatically means that it's not differentiable at this point. And if you look at it, it makes sense because you cannot find the slope of the point right here because it is disconnected. You could look at the slope of this point, the slope of this point, but it's not the same. So that's why this one is not continuous and it is not differentiable. If you take a look at this graph, it is also discontinuous. It has an infinite discontinuity because these graphs, these lines go on forever, but they never touch right here. So because it is not continuous, it is also not differentiable. And if you look at it, you cannot take the slope of the line right here because the line simply does not exist. This third graph right here has a whole discontinuity. And so because it's discontinuous right here, the point's way down here, or sometimes the point might not be there at all, you cannot take the slope of the line right here. So therefore, these graphs are not continuous, and because they are not continuous, they are not differentiable.
I may be a blind man, but I really wish I knew what this Christmas tree looked like.
Well, the line formed by the Christmas tree lights is actually continuous.
Oh, so that must mean it's differentiable, right?
Well, one would think so, but because you're blind, you may not know this. So actually, the lights form a cusp at the very top. So while it's continuous, it's not differentiable.
Huh. Once again, as a blind man, I really am tormented by the fact that I cannot see these Christmas lights.
Here, let me help you out with that.
Why are you following me?
So we know that this line right here formed by the Christmas lights is differentiable.
Really? So that means it's continuous, right?
Exactly, because every differentiable line is also continuous.
Wow.
Okay, so when do derivatives not exist? There's 3 instances where a function is not differentiable at a certain point. The first one is a vertical cusp. So basically at the point in reference, there is a vertical tangent line, so therefore there is no slope, making it not differentiable. The second case is a sharp corner, such as seen in the second image. Because there can be a variety of tangent lines, various slopes at that specific point, we can't say it's differentiable. The third one is much bigger. It's any form of discontinuity. So the first kind is a removable discontinuity, which is a hole. The second one is an infinite discontinuity, an asymptote. The third one is a jump discontinuity, where basically one line jumps down to another. So which of the following is differentiable at the point x equals a? The easiest way to go through this is to go through each answer choice and look at the tangent lines. So looking at the first choice, we see that we're at a corner here. We could have a lot of different tangent lines at this point. We could have one like this, and a bunch of different other possibilities. Therefore, we can't say it's differentiable because there is no definite one answer slope for our tangent line. So looking at the second choice, we see here that we have a discontinuity. We have a removable discontinuity in the form of a hole. Therefore, we can say this isn't differentiable at x equals a because it's not continuous. Looking at the third answer choice, we see we have what looks like an exponential function here with a point at x equals a, and the line continues to travel through it. We could draw a tangent line to this graph. Therefore, this one is most definitely differentiable. And then looking at the last answer choice, we see here that we have an infinite discontinuity in the form of an asymptote at x equals a. So we will not be able to draw a tangent line here. Okay, which of the following functions is not differentiable at x equals 0? So the best way to go about this is to think about the graph of each of these functions. So looking at choice A, if we can imagine an absolute value function, we would have a V shape. Looking at f of x equals 2, we know we would just have a simple straight line. So we're looking at x equals 0. On this first function, we can see that it's a V shape due to how an absolute value function is. So we know we have a corner here. Therefore, we can't create a definitive tangent line. Therefore, this one is not differentiable. In answer choice B, we have a continuous straight line. Though our tangent line will simply be, oh my god, what is our tangent line?
2.
To this?
Yeah. It's the same thing.
Though our tangent line will be 2, it still exists, therefore making this one differentiable. Okay, so at which x value is h of x differentiable? So we need to be thinking about our conditions for when we cannot take a derivative. Looking at point A, we see that there's a corner right here, so we cannot take the derivative here, so it's not differentiable. Point B, we have an asymptote. There's not even a line to take a derivative of here, so we know this can't be it. Looking at point C, we have a hole, a removable discontinuity, so we know it's not differentiable because continuity is a condition for differentiability. Looking at point D, this is just a point on a continuous line that keeps going, so we know that point D is differentiable.
Hello, it's money day, the day in which I give you money.
That's so great.
Here you go.
Wow.
Have a good day.
I can't wait to add this to my money tracking board where I can track all my finances responsibly.
We here at the Finding Instantaneous Rates of Change Company have really appreciated your hard work. Here's this year's salary. The raise.
Oh my goodness. Great. I can't wait to add this to my money tracking board too. Oh wait. Now I can't find the instantaneous rate of change because I have a jump discontinuity. What am I gonna do now?
So imagine you are asked to estimate the derivative at a point, but you're not given the function. Imagine you're given like a graph or a table or a set of data points instead. How would you find the derivative at that point that it's asking you for? So when this happens, you want to look at the points immediately before and after the point in question, and find the average rate of change or slope between them. So take a look at this graph. Here's the value you're looking for, f of a. You want to find the slope of it. So you look at the points immediately before and after it, and you want to find the average rate of change between the 2 points. And so the slope here is going to be roughly equal. It won't be the same, but it'll be a good estimate of the slope at this point. So by finding the average rate of change between the points before and after this point, you're effectively finding an estimate for the slope right here. And that's all this stuff is basically saying. Now let's take a look at some more example problems.
So let's take a look at this first problem. So the problem is asking us to find the derivative of this function at this specific x value. Now before, what we've been using is we've been using the definition of a derivative to evaluate this, which is the formula, the limit as h approaches 0, f of x plus h minus f of x all over h. But there is actually a simpler way of using this, because using this, it finds the derivative equation, and then you have to plug the point into that equation, which is just a lot more complicated than if you use the formula we've discussed in the notes, because all you're trying to do is find the derivative for this specific point, not the whole function. So what you can use is you can use the formula, the limit as x approaches a, f of x minus f of a all over x minus a. A is your constant. In this case, a is 1, because 1 is the point you're looking for. So to solve this, you do limit as x approaches 1, 1 is a, you plug 1 in for a. Then f of x is your function, so you plug in your function. And then f of a, you plug in your function with the constant, or the x equals, plugged into it, x equals 1. And then you simplify this as far as you can. So you get 3x squared plus 8 minus 11 over x minus 1 equals 3x squared minus 3 over x minus 1 equals 3x squared minus 1 over x minus 1. 3x plus 1, x minus 1, x minus 1. And you're left with the function 3x. Well, let me write this better down here. You're left with the function limit x approaches 1, 3x plus 1. So you get here, you're not done yet. What you want to do is you want to plug your constant into this x value of your simplified equation. So what you get is 3 times 1 plus 1 equals 3 times 2 is 6. So this is your derivative of this function at x equals 1. So f prime of 1 is 6. Now something I want to mention again, I know I mentioned this in the notes, but it's really important. The function that you get right here, that is not the derivative of f of x. That is not the derivative of f of x. That is specific to whatever point you're using in this equation. So if you were to use a different point, like x equals 2 or x equals 3 or any other number, this function right here would change. So you cannot use this every time. It's only specific to whatever point you're doing. So in this problem, you're asked to estimate the derivative of the point at x equals 2. So the point would be right here on the graph. So one way that you could do this is you can find the average slope between the points immediately before and after the point you're looking for in order to get the closest estimate you can of the slope right here. So if you find the average rate of change from this point to this point, which you would use the formula f of b minus f of a over b minus a, which in this case would be f of 3 minus f of 1 all over 3 minus 1. And then you were to simplify this further. F of 3 is 2, f of 1 is 0. Then you have 3 minus 1, which is 2. So you're given an average rate of change of 1. So the slope, or average rate of change between this point and this point, is 2. And so you can use this slope and say that it's relatively close to the slope at this point. So the derivative of f of 2 is roughly going to be approximate to 1. So in this problem, you're supposed to estimate the derivative at x equals 4 given the table of b of x below. So it wants us to find an estimate for b prime of 4. So one way that we can go about this is to again estimate the average rate of change between the points immediately behind and after the point in question. So the way we do this, so the points are f of are 5 to 9, 9, and then you have 3, 16. The average rate of change between these 2 points is 16 minus 9 over 3 minus 5, which is 7 over negative 2. So the rough rate of change between the points before and after the point in question is 7 over negative 2, or negative 7/2. So we can say that the derivative or slope at b prime of 4 is roughly going to be equal to -7/2.
Man, what a beautiful day. And I sure do love playing with this ball. It's my prized possession, of course. Oh my gosh.
To get your ball back, you must estimate the velocity of the ball 1 second after you have dropped it from a height of 3 meters.
I know how to do that. I'll use the definition of the derivative at a point. So, derivative fairy, I've solved your little riddle. You see, I used the definition of the derivative at a point in order to find the instantaneous velocity of the ball as it fell. So, using the position formula that we knew, which was 3 minus 5t squared, or function, I managed to use the limit and simplify it all down to the point where I got -10 meters per second. Now give me my ball.
Very well, my child.
Where's my... This isn't even my ball.
Farewell, my child.
Where'd he go?
IVT. What is the IVT? The IVT is known as the intermediate value theorem. It is a theorem which states if a function is continuous over the interval a to b, and w is some number between f of a and f of b, then there exists some number, c, between a and b, such that f of c equals w. This can help if you visualize it in a graph with the x inputs here and the function of those x inputs on the y-axis. So basically, if this line is continuous and all points along here must exist, there must be some point along here where this altitude exists. It can help if you use practice problems to visualize it. It can also be used to determine if a certain value, such as a 0 of a function, falls within an interval of that function, assuming it's continuous. This example shows that f of x equals x cubed plus x squared minus 46x plus 80 has a root somewhere on the interval 4 to 6, assuming it is continuous. F of 4 is -24, f of 6 is 56. So since that crosses the x-axis and goes a significant distance in either direction, we can assume that there must be some value, c, between 4 and 6, such that f of c is 0. IVT can also be used with tables. In this case, if you're trying to find where a 0 exists on this interval, you're going to want to see where it changes, where f of x changes signs, like between 3 and 4. It goes from 3 to -2, so the one between 3 and 4. And over here, 4 to 5, -2 to 1. Also would have a 0, and 6 to 7 changes signs again, so you'd have a 0 there as well.
So this practice problem, we're trying to find if there's a 0 on the interval of 2 to 4. This is our function here. As you can tell, finding how to find functions are continuous. This function is continuous. So that means we can use the intermediate value theorem to find if there's a 0. So to find if there's a 0, first we have to find h of 2 and h of 4.
h of 2 is 4 plus 14 minus 30 equals negative 12. And h of 4 is 16 plus 28 minus 30 equals 14. And using that, we can see if 0 is between those two endpoints of the interval, and it is. And that is essentially proven that a 0 is between this interval, because we have found the endpoints, and 0 is between those, and also it's continuous. So we can prove that there's a 0 in the interval. That's what intermediate value theorem can help you find. So this is a very similar problem to the last one we've had. We once again have a polynomial, and we're trying to find if there's a 0 on the interval, in this case from 3 to 5. Because we have a polynomial here, we can know that it's continuous, and because we know it's continuous, we can start to use the intermediate value theorem to see if we have a 0 between 3 and 5. So the first thing we're going to have to do is we're going to have to find the d of 3 and d of 5. d of 3 is 15, and d of 5 is 3. So if you write this in an interval of d of x, you find that 0 is not between these. If you use intermediate value theorem, this doesn't mean that there is no 0. There could potentially be a 0, depending on the, if we fully graphed out the function, there might be a 0 on that interval, but this is just saying that we can't prove there's a 0, and we would have to work further to find if there was a 0. So our third example problem here, we aren't presented with a function, but we're instead presented with a set of x values and a set of g of x values respective to each x value. We don't have to worry about it being continuous, it's kind of assumed here, but we can find now between which of these there's a 0. Between 6 and 10, those are both positive, so there's not going to be a 0 there. Between 10 and negative 2, it does change signs, so there's going to be a 0 between 1.2 and 1.3 somewhere. Between negative 2 and negative 8, there's not a 0 there, as they both are negative. But between 1.4 and 1.5, you do have a 0 between negative 8 and 5. So when you have this, you want to take your final answer, you're going to say g of x equals 0 at x equals, oh no, not at x equals, but between 1.2 to 1.3 and 1.4 to 1.5.
Man, I sure do love people watching.
Yeah, me too. Especially like watching that weirdo that just walked behind the shed over there.
Facts. Wait, what happened? He was just behind. Do you think he stopped while he was conveniently out of sight behind that red shack over there?
Bro, he must have, because first he was moving left, then he was moving right. So by the IVT, he must have stopped sometime in between.
Oh, that makes sense.